Good morning, good afternoon, or good evening. We're now on question 8 of the Step 3 2024 paper. As with all of these videos, hopefully you've had a go at this question already and you've either been successful and you're looking for other ways that the question could have been attempted, or you've got stuck and you're looking for some hints. As with most of these questions, I've not worked through them already. I haven't got solutions prepared. This will be a blind work through of the question where you can see the kind of the mistakes and the thought processes that can happen in such a question. This one is our last of our pure questions, and often question 8s of these papers include some completely new idea or concept. Not really on this one, although you will see the idea used in 8 part I may get used repeatedly throughout the question. So let's jump straight in. 8 part I, we have an equation which is written as a double bracket. And we've been asked to say something about what this equation really is. And it wants to be shown that it's a pair of straight lines with gradient of plus or minus 1. Well, if you have two things that multiply to 0, one of those things must be 0. So and because it's a show that I'm going to add a bit more detail to my answer, as the product is 0, that means one of the brackets equals 0, so either y minus x plus 3 equals 0 or y plus x minus 5 equals 0, i.e. the equation is equivalent to y equals x minus 3 or y equals negative x plus 5, two straight lines. Which is quite a nice concept, if nothing else. If you want to put two graphs onto the same picture and you want to describe both the graphs at the same time, then rearrange them both to equal 0, multiply them together to make 0, and you can basically combine any two graphs into one graph with this quite simple trick. So now second part of part I, show further that that equation represents a pair of straight lines with those gradients if and only if that condition holds on P, Q and R. Okay, well we're basically taking the example we've already got and taking it one step further. So two straight lines y. Now how do I want to write it is the next thing. So I'm making various choices here. Yeah, I'm just going to say y plus x plus a equals 0 and y minus x plus b equals 0. Not convinced this is the best way to tackle this part of the question. Two straight lines of gradients plus or minus 1 combine to, so our combined equation is as so, and you can see this is near identical to the first part, but I now don't know what the plus 3 and the minus 5 are. Well, if I expand that out, that's equivalent to y squared plus, y squared minus x squared minus x squared. We're going to have plus 2ay plus 2by minus 2ax plus 2bx. And what's my final term? I've got an xy term in here somewhere. No, I don't, because the xy terms cancel. We kind of got dots going on there. Plus the AB. If I've got 3 terms times 3 terms, I should expect to have 9 terms. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why have I got too many terms? Oh, because there's not 2 lots of each of these. I was in expanding double brackets form where the middle ones kind of double up. These ones do not. We only get an AY once. So how many terms do I have? 1, 2, 3, 4, 5, 6, 7. The minus xy and the positive xy, which have cancelled out. Okay. Equals 0. And if we compare that to what we have, that's equivalent to the p being equal, p is the coefficient of the y, a plus b. The q, which is the coefficient of the x, a minus b. And the r, which is the constant term, being ab. So now p squared minus q squared can be expanded and simplified. Is that thing, which is a squared plus 2ab plus b squared minus 2ab plus a squared. The a squareds and the b squareds cancel. I'm left with 4ab, which is equal to 4r. So if we were 2 straight lines, we've shown that that condition holds. Now, if that condition holds, then have we shown that we can factorize? So we've shown that 2 straight lines implies p squared minus q squared equals 4r, and conversely, if p squared minus q squared equals 4r, then we hopefully should be in the position where we can factorize that statement. Is that immediate? Well, we can pick, well, the A, I could pick the A and the B, and then what we've shown above will indeed work. So A we can pick to be, if I subtract these, which way around do I want to do it? I want to do P minus Q. So this is going to be pick A to be P minus Q over 2, and B as P plus Q over 2. Then AB equals P squared minus Q squared over 4, which is exactly R, and the above shows the equation factorizes. Probably gone into a little bit more detail here than is necessary. Factorizes into 2 straight lines of gradient plus or minus 1. And maybe gone a bit deep into that if and only if condition. We probably could have just got away with putting some simpler words after the forward statement. In the remainder of this question, C1 is going to be an equation of that form, and C2 is our normal quadratic. Well, one thing I want to do near immediately, even if it doesn't become useful later on, I really want to complete the square on this C1. So before I even go any further, I'm going to say that C1 could have also been written as y plus s squared, which would have given me the y squared, would have given me the 2sy, gives me an s squared, but I have an extra plus s. So there's an alternate form that might be useful for C1. So part 2 of the question now. Part 2, explain why the coordinates of any point which lies on both of those curves also satisfy that equation. Okay, well, what is that equation? That looks a little awkward, but really, if we look too closely, this part is simply this rearranged to equal 0 plus some multiple of this thing equaling 0. So C1 is going to imply that y squared plus 2sy plus the s plus 1 minus x equals 0. C2 is giving me that y minus x squared equals 0. So if I take equation 1 and add on k lots of equation 2, I get exactly the equation that they're considering. And that feels quite odd, because I've not really got any closer to solving this simultaneous equation. I've introduced an extra variable for any k. So I've included an extra thing. I've made it a lot worse of an equation. There's better information here than there was in this new one. But this new equation is of the form that we've already considered in part I. It's a y squared, not quite a minus x squared, because it's got the k there, but it's going to be similar. Given that s is such that these equations intersect at 4 distinct points, show by choosing k equals 1. Okay, so we're going to choose k equals 1 to make it negative x squared. Gives an equation representing a pair of straight lines on which all 4 points of intersection lie. Okay, so let k equal 1, and I'm going to call this equation star because I feel like I'm going to refer to it a few times. So equation star I'm now going to write as y squared minus x squared plus, and I want the y coordinates together, 2s plus 1 y minus x plus s plus 1 equals 0. So now it looks even more like 8 part I. Given s is such that these intersect at 4 distinct points. Well, how can I show that this has 4 distinct points? Because I'm not always, well, maybe I am always going to be able to factorize this. So, as in part I, let p, or p is the coefficient of the y. So my thought now is maybe this condition is always satisfied. If that condition in the first part is always satisfied no matter what, then I'm always able to factorize this in the way that's needed, and then we can do some geometric argument. That means it's going to work. So I need to check that p squared minus q squared, yep, then p squared minus q squared is equal to 2s plus 1 squared minus negative 1 squared, which is 4s squared plus 4s plus 1 minus 1, which can be written as 4s, s plus 1, which equals 4r. So by part I, star is 2 straight lines with gradients plus or minus 1. Okay, so now why does that mean that all 4 points of intersection lie on this? So any intersection lies on both C1 and C2, but from C1 and C2 we created this equation star, so must satisfy star, but star is 2 straight lines, so lies on those straight lines. Okay, nice. Again, quite a weird situation we've got ourselves into. We've managed to restrict where these intersection points are living on these two things. Part 3. And I'm going to turn the page now. So part 3 is now trying to actually put a condition on the S. So part 3. Show that if they intersect at 4 points, then we have a condition on S. At this point, I kind of want to look at what these curves actually are. C2 is the easy quadratic curve. It's just y equals x squared. So C2 is that curve. Now C1 kind of has flipped the x and the y, and actually having C1 in its completed square form, it I think is a little bit more obvious what's going on, because this can now be thought of as a transformation, but all of our x and y's are backwards. So if this was just x equals y squared, it will be a quadratic as so, a quadratic of x in y squared, so it's kind of the wrong way round. But we've put a plus s in. Well, that's going to move my quadratic down, and then I've added s to all my x coordinates. So I think this quadratic is going to be something like this, which is kind of awkward, where this coordinate here is s, negative s. I'm saying it's a bit awkward because these look like they miss. But I made the assumption that this s was positive. If this s was positive, that's where that quadratic C1 is going to lie. And you can see the condition we're trying to show is this s is actually going to be less than negative 3/4. So actually it's going to be over here and up here. And now we can see, well, we still see we've only got 2 intersection points at the moment, except I have drawn that minimum point. The minimum point will be here. Still only 2 intersection points, unless that minimum point has actually got even further and is maybe over here. And now I can see that I do indeed have 4 intersection points. So that's what I've got now in my head, excuse me, visualizing this situation. And maybe that visualization is going to help me find a condition on that S, because this point here is going to then be, that one was positive S and this one was negative S. And of course we now realize that this S has to be a negative number, so those are in the right places, even though they do look a little odd. So what does that mean? Well, that kind of means that the minimum point the minimum, the furthest left point has to be below this curve. So I need, and I think that's about it. If I move this shape around in all sorts of different positions, then if that minimum point is in this section, I'm only going to get 2 solutions. If the minimum point is over here, well, I'm getting no solutions. But as soon as the minimum point is on this side of the curve, am I always going to get 4 solutions? Not necessarily, because this point here could be too low. So I could draw the picture with the minimum point maybe here, and I do only get 2 solutions again. So what exactly do I require? So I require that the vertex of C2 is under C1, and I'm going to require that this point here is positive, and both roots, again I'm thinking of this a little backwards because my x and y are reverse of C1, both roots are positive. And then that will ensure that I do intersect at 4 distinct points. Okay, so let's work out some of these things. So the vertex of C2 is, and that's why I've got this form here, that tells me that my y coordinate is -s and my x coordinate is s, which is exactly where I've drawn the vertex in the picture. So that means that that has to be under. So when I sub it in, we require that y is less than x squared. So -s is less than s squared. That's quite a boring equation. That's going to give us the quadratic s plus 1. So that means that s is less than 0 or s is greater. Nope. We've got solutions of 0 and -1. And we want this quadratic to be positive, so s is greater than 0 or less than -1. Which isn't going to give me the condition of -3/4, and is actually worse than that. It's giving me something that the s being less than -1 is quite an unfortunate situation. The vertex, does the vertex have to, yes it does have to be underneath that curve. Have I got the vertex wrong? No, the y coordinate is -s, the x coordinate is s. I've got the right quadratic. That quadratic does have solutions of 0 and -1. I want the quadratic to be bigger, so that is saying that s is positive, or s is less than -1. Now, what exactly do those conditions mean? If the s is positive, that means I'm over here. And yes, indeed, that vertex is below. So no matter what happens on that side, that does make sense. I'm worried because part 4 is the reverse. Part 4, we need to show that if s is less than -3/4, then they intersect. And right now, my condition has to be worse than this. So try and do this other condition, both roots are positive, and see where that takes me, and then come back to this condition. Because that's, yeah, something about that condition then isn't working. So I'm going to sideline that working and think about both roots. So we're going to have that, so we let x be 0, so then y plus s squared plus s equals 0. So this is plus or minus the root of negative s. So that does mean that s has to be negative to even have any solutions, but that's fine, we were expecting that. So this is negative s plus or minus root negative s. Again, I'm not getting the 3/4. I'm not getting the 3/4 in here. Now I'm looking back to think whether my rewriting of this was correct, which I'm pretty certain it still is. Okay, so let's take this to its logical conclusion. So we require negative s minus that to be greater than 0. So that's negative s is greater than the root of negative s. If I square both sides, need to be a little bit careful. So I'm timesing, saying s squared is greater than s. Well, greater than negative s, which is the same condition that I had up here. So actually, if the vertex is under there, yeah, because the vertex is heavily linked to where this shape can be. Basically, the vertex is on the line, y equals negative x. So if the vertex is in the right place, then automatically we have, well, we've now shown automatically that we have the roots in the right place. So we haven't actually gained any extra information here. And this is really awkward now. So we have this condition, we can reject s greater than 0, because then there are no roots to C1 and C2. So there's no intersection between those two if s is greater than 0. So why am I getting -1, not -3/4? Well, certainly, I have actually done part 3 here. I've shown that s has to be less than -1, so certainly s is less than -3/4. But if I'm trying to show this is an if and only if statement, which is what part 3 and part 4 combine to be, then I can't be implying that s has to be less than -1. That's gone too far. Is there something in the previous part that I could have manipulated in some way? Certainly I can try and find the 2 straight lines that this factorizes into. We've seen that we can factorize, and actually up here we gave the exact way to break those down. So I might do that actually. So now star we can write as, well, the a, I said we should do the p minus the q and half it, so that'll be s plus 1. And the a in my setup was with the positive, so y plus x plus s plus 1. And then the q is when I add these two together, then that's just plus s equals 0. If I do imagine expanding all this out, I get the sy and another sy. I'm getting the s plus 1. I'm getting the minus x. Am I getting anything that I don't want? No, because the sx and the sx both cancel each other out in the same way that the y's did before. So it looks like that's what my equation is. And now this gives me another way that I can actually tackle part 3. So then over here, if I think this is all unfortunately unpleasant or unrequired, I might think about going back to that later. But if I think of the alternative way, so part 3, the intersections lie on y plus x plus s plus 1 equals 0 and y minus x plus s equals 0. I think those were the two brackets I just created. Indeed they were. So basically what I can do now is sub these back into one of the originals to try and find the quadratics that come from each of those, each simultaneously with C2 give quadratics, and these quadratics are going to have two solutions each, because otherwise they if we don't have two solutions, we have to have 4 solutions in total, so we need 2 solutions from each of these 2 quadratics. So the 2 quadratics are going to be, and I've chosen C2 because it's so much nicer. So from the first one, rearranging to make y equals the x squared. So this one's going to be x squared plus s plus x plus 1 equals 0. And the other one is x minus s equals the x squared, or x squared minus x plus s equals 0. Both of which need 2 distinct solutions. And this way I'm actually a lot happier because I know the discriminant gives me a 4. And I wasn't getting that 4 with my other method. It implies that b squared minus 4ac is strictly greater than 0. I don't want a repeated solution because I want them all to be distinct. So that's going to mean that for the first one, 1 squared minus 4 lots of s plus 1 is greater than 0. So that's going to be minus 3 minus 4s is greater than 0. 4s is less than minus 3, or s is less than negative 3/4. And the other side, we're going to have, this time, negative 1 squared minus 4s is greater than 0, or 4s is less than 1, s is less than 1/4. For both to hold, s must be less than negative 3/4. So it's much easier, for what we've shown here, it's much easier to get 2 solutions out of this equation than it was to get it out of this equation. That kind of makes sense with the picture that we were drawing. If I were to draw that picture, we're getting 2 solutions from one of the branches very, very easily, which is this version here, whereas it's harder to get that second set of solutions. Okay, so that was actually way more pleasant than I was making it out to be with the graph. But now we need the converse. So if s is less than negative 3/4, then we intersect at 4 distinct points. So if s is less than -3/4, well, can't I just do this argument? We've shown that that equation star, we've shown that this equation, actually independent of the s, can always be factorized into two straight lines. So we just need to find those points of intersection. So if s is less than -3/4, recall the intersections. Now, yeah, any point of intersection is going to lie on these two straight lines. Is that enough? Because we've created this equation from, yeah, and this was the comment I half-baked a moment ago, in that these two equations do imply that equation star, but that equation star might not lead backwards, because these two carry more information than the equation star does. So we can't really use the equation star to go backwards. So what are my alternatives? I could try and solve these properly, as in sub this y in, and then I'll get an equation in x to the power 4, which is awkward because I kind of want that to be a quadratic of a quadratic. So I want it in terms of x squared, but we have this minus x. And working out the conditions on a quartic to have 4 distinct solutions, while possible, you can think about its stationary points and where its stationary points have to be, is not as easy. Is that my best way of doing it, though? Because I've certainly have that those two straight lines do intersect with C2 in 2 places, in 2 places each. Now I kind of need to show, so if that, the above shows C2 intersects, what were my 2 straight lines? Y equals -x, -s minus 1, and y equals x minus s twice each. But I also need those same points of intersection to work in C1. Now, I could name those points of intersection and show that they do indeed lie on C1. So let A be, I'm going to call this L1 and this L2. Let A, B lie on L1 and C2, i.e. let the coordinate AB. So that's B equals A squared and B equals -a minus s minus 1. And let's see if this satisfies C1. If I can show that this point satisfies C1 as well, then the points of intersection between this and C2 also intersect C1. I've got two of those, and I'll do the same with that as well. Again, there might be better ways to tackle this. So let's sub into C1. And I want to be careful because I don't want to assume the answer. So I'm going to start with the right-hand side of C1, which is b squared plus 2sb plus s plus 1. And I'd quite like for this to simplify down to just x, which in this case is a. So this is, well, this is a minus s minus 1 squared plus 2s plus s plus 1. So if I replace all the b's using that second equation, is this going to turn out to just be a? Now I'm worried because I haven't used this. Maybe I should be worried, maybe I shouldn't. I am going to have to use this because I'm getting an a squared from this term. So did I want to do this quite as heavy-handedly? I think I just have to go for it. So this is going to be a squared plus 2as plus 2s plus 2a plus 1. I should have 9 terms in total. Plus s squared is the last term I was missing. Minus 2as minus 2s squared minus 2s plus s squared plus s. So I'm going to be left with an a squared, which I could turn into a b if I wanted to. The 2as cancels the 2as. I've got a plus s squared, a minus 2s squared, and a plus s squared. I've got a plus 2s and a minus 2s. So what am I left with? Plus 2a plus 1 plus s. Nice. So then the a squared, so together these do imply that the a squared is equal to negative a minus s minus 1. That's negative a minus s minus 1 plus 2a plus 1 plus s equals just a, which equals the left-hand side, i.e. AB lies on C1. So the two solutions of C2 and the two solutions of C2 and L1 also lie on C2. That means that C1, C2, L1 intersect in two places. And now if we do the same, so let CD lie on L2 and C2, which means that the y coordinate equals the x coordinate squared, and the y coordinate equals the x coordinate minus s, which, now I know what's going to happen, likely means I'm going to use the fact that c squared equals c minus s. So now into C1, we are going to have at the right hand side, which I'm subbing the y coordinates into, minus 2 SD plus s plus 1. This one's going to be a little bit more pleasant because the equation is just that little bit simpler. C minus s plus s plus 1. So that's c squared minus 2sc plus s squared minus 2sc plus s squared. Oh, I've got... Oh, why did I swap the sign there? That's a plus. That's a plus, so that's a minus. And that other one was a plus. So that cancels with that. The s squared, I should have expanded this other bracket out at the same time. S squared plus s. The s squareds all cancel, and I'm left with c squared plus s, which is just c, which is the left-hand side. So CD lies on C1. So let's put this all together. So therefore, the four intersections of C2 and star all lie on C1, which means that C1 and C2 intersect in, and really I should say, at least 4 places, but star implies at most 4 solutions. I'm squeezing onto the bottom of the page again. It's a bad habit. So therefore, C1, C2 intersect in 4 places. Now, really, I should check that those 4 places are distinct. It's not too hard to do. The only way for them to be non-distinct is if the intersection between these 2 lines was a solution, which is when x would equal -1/2. So I just need to check that when x is -1/2, I don't have that becoming a repeated solution between the 2 cases. We certainly can't have a repeated solution within one case because we set the discriminant to be strictly greater than 0 all that time back. So really I should add that base of condition in. I'm not going to do that here though. But if you want to clean up the final section of this, you should. Hopefully that question, this video was helpful to you then. A little deep into the logic of trying to prove the forwards and the backwards. I am still kind of sad that this pectoral argument didn't end up working, and I might look back to see if there's another way to manipulate that argument to get the 3/4 rather than the -1 that it was falsely giving. There's some in there assumption that I've made which is false. There's some false assumption I made when drawing that picture. Just not sure what it is at the moment. To close off then, the rest of the videos in this playlist will have all the rest of the questions from this paper, and the next video below will be our first mechanics question. Good luck if you're attempting these yourself.